Hi, so we're going to go over the implementation of the myparser_lib. All of the answers are in the GitHub repo. We're doing it here so that you can see how these functions are implemented and they're not hopefully that mysterious. So the first thing we're going to do is remember the type of a parser is string, the function from string to maybe something, and the rest of the string. So the first thing we might want to do with a couple parsers is try one, and then if that works, try the other, and then stick the two outputs together. The first thing you should notice is that the output I've sketched looks a little weird because we have the first parser, we have the second parser, we have this input. Where's that coming from? Well, that's because this is really just this. So in the back of your mind, whenever you see a parser, remember that it's really just that. So the input is the input string that we're going to read in. So it seems hard until you think about it for a second, and there's really not a lot of choices we have. We have two functions. They each take as a string. We have one string. Well, we know we want to do one first, so let's do that. We have two outputs we need to handle. If the first parser fails, what do we do for the total parser? Well, we're going to fail. If we succeed, we're going to get back an A, and we're going to get back a little more input. And then what should we do? Well, we've got a string, and we've got another parser we want to run. So we'll take that parser, we'll run it on the rest of the input. Now again, we can fail. If that parser fails, the entire parser fails. If that parser succeeds, then we get back a B. We get back the rest of our input. And what do we return? Well, the shape of the output is fixed. We can either return nothing or just, but we've got both of our things, so we successfully parsed. We know we need a tuple of A and B. Luckily we have only one A and one B, so there's not much choice there. And we need the rest of our string. And we have three strings to choose from, but it's pretty clear that this is the one we want. So that's the first of the four functions that are going to make up our parser library. We also have literal. Literal is just going to parse in a string exactly. So again, we have two inputs, the string we exactly want to parse and the input. And again, remember, what are the different types of constructors? Strings are lists, so there are only two possibilities. Either we're trying to parse the empty string, and then something happens, or we're trying to parse the non-empty string. And same for the input. If we either have an empty input or a non-empty input. So if we're parsing a non-empty string from an empty input, what happens? Well, we don't succeed. If we're parsing an empty string from any input, well, it's a little unclear what we're going to do, so we're going to leave that empty for now. And if we've got a non-empty input and if we have a non-empty string and a non-empty input, well, how do we tell if this works? It's just by recursion. So if h equals hi, then we do something interesting. Otherwise, well, this isn't going to parse. If the string we're interested in starts with an A, and the input starts with a B, it's not going to work. So what do we do here? Well, we use recursion. Literal, well, we'll give it the tail, and the tail of the input. Now we've got two cases to deal with again. Nothing. Nothing, nothing. And just yes. And the rest of the input. Let's say we want to return just S, the rest of the input. There's a little bug here, but we're not going to know that till we test it out. Now, if we think about how this recursion goes, we're going to keep peeling off things from the head of each of the input and the string we're interested in until either the input string is empty or the head is empty. That means this has to be just empty string our input. Okay. We've gone too long without reloading the REPL, so let's try it. Oh, look at that. Mistakes already. So again, I have not turned off my tabs. So you've got to make sure you do that. Okay, now it works. Let's try to parse the literal. Hi off of hi with no with no space in front. So you notice it's kind of working, but we want to get our string back. We want to carry the information we care about through. So the one little mistake we have here is that we should be adding back our head as we go. And now we get back our high. If we try to test on things that don't match, we're going to have a problem. So these two combinators are enough to do some basically interesting things. We can have a literal, and we can parse that, and then we can parse another literal. So you can try these in your console to get a feel for what's happening here. Okay, that's a little interesting. I've made some hard-coded example parsers for you to get a feel. Here's a nat parser. It parses natural numbers. It looks a little bit worse than it is. All it's doing is saying, if I see a number, then I'm going to parse that number starting at 0. And we keep a count. Whenever we're finished, when we stop parsing a number, we're going to return the number. As long as we see the number, we're going to keep reading it in. And then we're going to use, we're going to multiply the thing we're holding on to by 10 to get the next thing. and keep building up our number that way. Oh, of course. So remember, you need to use strings when you do your parsing. So C parses the string 123 into the integer 123. Now we can start playing around with more interesting things, but that is a motivating example. For instance, we can create a positive float parser, which takes in a natural parser, then parses a literal period, then parses another natural number. We run this in our console. Well, it parses, that's pretty cool, but the output is a mess, because it's just tuples of the thing we're interested in, a string, and something else. There's got to be a way for us to turn the output of one parser, to massage the output of a parser into something we want. And we're going to suggestively call that map parser. And this is the third function we need for our library. It's going to take a parser, it's going to take a way to change the output, it's going to return the new parser. Again, this seems like it might be hard to write. But our parsers are just functions, and specifically a function that takes in a string. We have another function that has some other random stuff, and a string. So the only real reasonable thing to do is smash this parser into our input. Okay, so parsers can always fail. What happens when the parser fails? Well, the whole thing fails, no big deal. And if it succeeds, well, then we need an output. So our output should still succeed. And we probably want the shape of our output is gonna look like this. We can take we know the rest is probably going to be the same. We only want to change the output of the parser. We don't want to change how it reads things off the string. Now we need to change an A into a B. What's the only way to do that? The way to do that is F. Let's make sure I didn't make any typos. No typos so far. So this is a suggestively named math parser. You should think, could parsers be functors? Do they obey the functor laws? And we're going to leave that there for now, but this is very useful. I've written a few slightly buggy functions for demonstration purposes. So we can take our definition of a float before, use our map parser, and parse out the whole part, ignore the period, and the fractional part. So we can take the whole part and add it to, using some slightly buggy math, the fractional part. Now this gets kind of unwieldy on one line, so for parser libraries that work like this, it's often easy to break it up into multiple lines like this. And now we can take our float parser and run it, and you'll see we get a nice regular float right there. No weird stuff. Another thing that we might want to do is to alternate. Try one parser, and if that parser fails, try another parser. You've seen the either before a few times now, so if the first parser succeeds, we'll return an A. If the if the left parser succeeds, we'll return an A, and if the right parser succeeds, we'll return a B. And don't blame me for this notation, it's semi-standard. So we have our input, and we have a PA and a PB, and we're going to do exactly what I said. Right, we've got two functions that take a string and a string. There are only so many ways we can plug them together. So I'll do PA input of, well, and that always results in what? Nothing. If we get a nothing, what are we going to do? Well, that's going to be a little bit interesting, right? But we also get just. And if we get just, what do we do? Well, then we're done. We say it is a left. Sorry, we say it is a. Let's let the types help us. So we know it's a parser, so it's got to return a maybe. So just undefined. That's good. We know the next thing is going to be a tuple of something and a string. That's good. But we want to return an A, so let's stick the A right here. We got a type error. If you read this type error, you'll see that, wait a second, you wanted an either something, but you gave me an A. That doesn't make any sense. So remember, if we want to make an either, either has two constructors, left or right. So we got to use the left one. And now it works. And this bookkeeping is a little bit annoying right now, but it's what makes this whole thing possible. So if the first parser fails, well, we said we were going to try the second parser. And what input are we going to try it on? Well, we don't have access to this anymore because this didn't work. So we have to try it on the original input. If that doesn't succeed, well, that's pretty easy. The whole thing didn't succeed. If that did succeed, we get a B. And let's not make the same mistake again. We'll return right B. Wonderful. No errors. Now we can start to do some interesting stuff. So before we built up the functions from scratch, which you can always do, but isn't very convenient. Now that we've got powerful enough little language, we can start to build up. These little parsers without using the functions directly, just by combining their pieces together. So, for instance, an int parser is either a literal minus and then nat parser or a nat parser. And then we can map that nat parser, map the results into the thing we want. So let's try this. And again, we get the correct output. This is constructed specifically because it might be helpful for the homework. Now we can do a true float parser, which takes an int parser, a period, and a nat parser, and then does some slightly buggy math to convert that into a float. And more fun, we can take our old parsers and combine them into more general parsers. So this parser takes a float or int, it takes a float parser and the int parser, and it'll try to see if it's a float or if it'll try to see if it's an int. It's actually, because of the way that this OR works, it tries the first thing first and then the second thing, we need to have, if there's overlap between the two things that could parse, we need to have the most complicated thing go first. If you reverse these things and try the examples, you'll see a little bug. Okay, the last function in our little parser library is repeating, or rep. It's sometimes called many. It takes a parser and it parses it as many times as possible, getting the output into a list. So we got a parser. Parsers are functions that take in strings. We got a string. Hopefully you see the pattern by now. Say, try to parse it once. And if we parse it, if we don't parse it at all, do we succeed? Actually, I don't remember off the top of my head, so we're going to leave it undefined. Or if it's just, we get back an A, and we get back the rest of the input. And what do we do here? Well, we need to do a recursive call, right? So our recursive call, we'll take rep, it'll take the rest, it'll take our PA, we'll say case, repeat PA over rest recursively of, and that could fail, or that could succeed. And now this is a list of A's. I chose a bad name. Let's call this in1. And then we can call this in2. Well, if it works, we probably just want to keep this here. If it fails, we should probably keep it here. If it doesn't succeed, well, this keeps recursing, so it needs to hit a base case. So it always needs to succeed and return the empty list. So did I make any typos? Did I do anything dumb? I mean, probably. We'll see. So let's try it. Let's make a list of floats or ints. Oh no, where's my list? So, you may have noticed that there's a slight bug here. We never actually add anything to this list we're building up. So when we get this input, we better stick it on that list. Okay, now we've parsed our list of numbers and we've got some good data we can process with the program. But this is kind of a poor function because if there's things that are slightly unexpected, like spaces, the whole thing falls apart. So we've provided a space combinator, a space parser. It just eats as many spaces as it can get its hands on. In fact, it's often nice to have something called a tokenizer, which is a pun based on a more standardized parsing terminology, which just eats up the spaces before something and eats up the spaces after something, and then keeps the result of the thing in the middle. Now we can eat up tokens, float int, and our list works just fine. Finally, we've got a letter parser. Not finally. We've got a letter parser that parses letter chars. And we have a var parser that parses what, for this assignment, we'll consider a good variable. So a lot of these functions are written in somewhat clunky ways because they're the ways students in the labs have traditionally written them. But this is definitely not the only way to write many of these functions, and we'll see in the coming weeks that there are more elegant solutions. Also, if you find yourself wanting to do additional parser things over and over again, just make more functions and add it here.